time to start. Yes. Oh. Are you agreement? Are you going to count down? 5, 4, 3. Okay, please close the door. So, welcome to the Valgrind room. It seems to be full. So I thought it would be interesting to do a kind of retrospective talk about Memcheck. It's been around quite a long time now, and it's been something I've wanted to do for a couple of years, so now is an opportunity. There's a couple of things I'd like to say before I start. Firstly, this is a kind of personal view, my view of how things went and how things might go in the future. So I don't claim to represent anybody. I don't claim to be sort of neutral or fair or unbiased. It's just my views about it. The second thing I'd like to say is that Valgrind and Memcheck is the work of a whole bunch of people, sort of hard-working, talented people, and I want to acknowledge everybody that's contributed to the thing at this point, because I kind of speak of some history, but it's been influenced by a lot of people. So this is a rough overview of the talk. I just want to show you approximately what it does, so everybody has some idea where we're going. I'll talk quite a bit about some history, and then talk a little bit about what the design is. Then talk about some problems with the current design, and then I want to look forwards a little bit and talk a bit about the relevance of what we have now and some opportunities. And it's hot in here. I think putting the windows on tilt would be good. Maybe. No, tilt. Up. Jump more. Okay. Yeah. Yeah. So what it does, you can think of Valgrind or Memcheck as being a process-level virtual machine. It runs your program from the very first instruction, and basically does two things. It observes all memory references and checks them, and it observes all malloc and free calls, basically memory allocation. It also observes memory allocation via movements of the stack pointer. So it's going to check that each access is allowable, and you want to make sure that if you are using undefined data, which you often are, even if you think you're not, that doesn't cause any observable bad effects. So it's actually very simple. It can only really do two things. It can tell you that you're reading and writing memory in the wrong place, and it can tell you that you are using uninitialized values. So here's some simple examples written in C, but we can speak C++ really if you like. You allocate a block of memory and then you access off the end, possibly reading it, it complains. You allocate memory and then you free it, but then you still access it, it complains. You allocate some memory on the stack presumably, and then you use the value from it which is undefined, so it complains. And then, as a kind of a useful side effect of observing malloc and free, you allocate some memory and then you just throw away the pointer, and it also complains. So that's pretty much all it does. And there's a lot of complexity for that. So I think if you've used the tool, or the tool suite, then you kind of understand that already. So I want to talk quite a bit about some history of the thing. And in particular, where did this come from? So, like many open source projects, this was a sort of started as a scratch and itch thing. In the mid-90s, a long time ago now, I was doing a bunch of data compression hacking, and I didn't like the fact that I didn't have a way to check, my code for the problems that we just saw. Particularly because you want your data compression programs to work reliably. The other thing was, later in the 1990s, there was KDE, and KDE was really cool. And I loved running, pre-release versions of KDE1 on old Spark boxes. I had a Spark Solaris box at the time. And they were a bit crashy, so I thought it would be nice to have a tool which helped the KDE people and anybody else to de-crashify KDE a bit. So I was working as a compiler writer at the time, and I started writing machine code interpreters, which seems a rather strange thing to do nowadays. But I found that a machine code interpreter, x86 interpreter, is kind of slow and inflexible. And if you want to make it flexible, it's even slower. So I thought, let's do a just-in-time compiler, because that's the cool new thing back in 2003, 2004. At least it was a cool new thing to me. So I kind of borrowed some ideas about doing just-in-time compilers. And from Glasgow Haskell, which I was working on at the time, I borrowed the idea of having a simple intermediate representation from which you translate a very complex source language. And that makes it much simpler to deal with. And you can also type check the representation. So it's easier to make stuff reliable. Another really source of inspiration was a book by Chris Fraser and Dave Hansen, I think, called Retargetable C Compiler, which is almost forgotten now, but it was a really amazing book, and if you have an opportunity to get it, you should, if you're interested. But one of the things they argue is that complex code generators are mostly not worth the hassle. You get 80% of the performance from 20% of the complexity. So these two things really inspired the core of Valgrind. So sometime around 2001, I basically quit my job and spent 10 months hacking on Valgrind, or what became Valgrind 1, version 1.0. It came out in the pre-release phase for KDE 3, and there was a lot of back and forth with the KDE developers, which was very beneficial for Valgrind, because they would take a pre-release version of Valgrind and try it out and say this doesn't work or that doesn't work, and tell me a whole bunch of stuff I didn't know about, particularly for C++. And I think it was helpful for them because it allowed them to, for the first time, to have a free tool which would tell them, when they're using freed memory in particular, and stabilize their system. After 1.0 came out, there was a bunch of key developers joined, so I was extremely fortunate to be joined by people who understood a lot more than I really understood. In particular, I only understood compilation aspects, and I didn't understand anything much about the aspect of making a virtual machine that dealt with the Linux kernel. So there was then a phase of kind of a rework and redesign where everything was basically rewritten. We had a new JIT, we had a much better handling of system calls and signals, and to some extent threads. And we got also, from one of the key developers, early people, a proper tool interface. So it used to be just one lump of code which did memory checking. It then got partitioned into the Valgrind core with a clean interface, so you can build tools on top of that, and the tools are relatively simple. So the new tools were CacheGrind, a cache simulator, which is still there. In fact, they're all still there. Massive, a heap profiler, and CallGrind, which is a kind of version of CacheGrind that understands function calls. And sometime late 2004, I guess, there was, I think, our first new port to the then new 64-bit x86. It's a whole big deal in itself. Since then, we've had a whole bunch of new ports after that.
So the original was Spark or?
32-bit x86. Yes. Spark is just coming now.
So these also didn't work on Spark? Because you said you started with Solaris.
Oh, that was kind of before, yes. KDE kind of morphed from Solaris to mostly being Linux. I had a Spark box at work and a PC at home, so you know, you drift to x86. I think a lot of people did. So there were some initial design goals, and for me, I'd become rather disillusioned with toy tools in the kind of early 90s as a grad student. So the thing I really didn't want to do is I didn't want to build another toy tool. So it has to scale, and of course it has to run KDE, and it has to run GNOME, to be fair, and it has to run OpenOffice, as it was called at the time. So I used OpenOffice as a kind of destruction test of early Valgrind. So OpenOffice is good because it's extremely big, and it contains a whole bunch of threads, which are, again, in 2003, 2004, a relatively not so mainstream thing, which has since become important. Later, I wanted to run Firefox, and Firefox is an even more stressful test than OpenOffice, mostly because of it generates a lot of code itself. I wanted to have a tool which had basically 0 false positive rate. So I didn't, if it reports an error, that, you know, particularly an undefined value error, that must be true. Tools which have high false positive rates cause a lot of time wastage for developers trying to figure out which of the reports are true and which are not true. And they eventually cause the developers to stop trusting the tools and stop using them, or that is a serious danger. At the same time, I didn't want to have a high false negative rate, so I wanted it to be reliable and, you know, pick up most bad stuff. Should be easy to use, so no recompilation, no relinking, no nothing. You need debug information, but you don't even need that. You can just run any executable. And then there was a sort of an interesting meta goal, which is that, at least for me, and I think for many of us, we always wanted to have influence, which is to say we wanted to change the expectation of C++ developers in the open source community. This was really the first, I think, free tool that did memory checking in a widespread way. And I wanted to have it so that when I take a piece of code from you, you know, a C++ module, I actually expect that there's no observable memory errors in that piece of code, to the extent that you can verify that. So I kind of wanted to increase the level of quality of expectation in a way. So how did we do this? Well, one of the things was we built the crappiest system that actually worked, and when it broke, we fixed it rather than trying to over-engineer it, I think. At least for some parts of the development cycle around the 1.0 release, that involved almost daily interactions with KDE people who said, it broke, and then I fixed it, or we fixed it, and then they said it broke again, and we fixed it, and this was a kind of really good interaction. A couple of other random points. I always wanted to have assertions on all the time, and I think that's been a beneficial thing. So you can't actually build Valgrind with assertions off. It has a lot of assertions, and we budgeted, I don't know, I kind of mentally budgeted something like 5% performance loss to have those assertions on all the time. I think that's actually been a good thing. It's actually quite hard to make Valgrind crash or segfault, but you can make it fail with assertions quite easily. I'm not sure that's completely true, but that's the impression. We had a lot of good advice about how to do some stuff. We also had some not so good advice. One of the things that did, which was very stupid because of my naivety, was didn't know what to do about threads. And threads, we couldn't really avoid them. So somebody told me, somebody who shall remain nameless and is not here, told me, write your own libpthread.so and insert that into the process instead of the standard glibc one. And then you can under the hood direct threads in your system. And version 1 of Valgrind actually did that. It was completely insane, and it's actually not possible really, because libpthread is so kind of connected to glibc that you can't really replace it. Now we have a slightly less stupid hack. I'll get to that later. Well, at least threads work, sort of. So along the way for Memcheck, we did some, we experimented with some basic design decisions. One of the basic design decisions is we are tracking undefinedness. Should we use, for each byte, should we track it, represent its undefinedness with 1 bit or 8 bits? So tracking it with just 1 bit per byte is kind of attractive because it means there's much less data to store. But what it means is that you cannot ever accurately deal with code which does bit fields. So if you have a byte where some bits are initialized and some or defined and some are not, then you have to say, well, we're going to represent it as totally defined or totally undefined. And there's a lot of code that deals with a lot of bit fields. I tried this, and what you get is thousands and thousands of false errors, either false errors, or if you put it the other way, you miss lots of errors. So it's like, okay, we're going to do 1 bit per bit shadowing, even if that's expensive, because we need that to get a really accurate system. Another question is, how shall we arrange the shadow memory, the tables which tell us which parts of memory are initialized and are not? So for every byte of memory, you need to know 2 things. You need to know, can I actually access here? So that's 1 bit. And what if I can access here, what are the definedness of these 8 bits? So in a naive implementation, you wind up having to have 9 bits per byte of shadowing, which is actually quite awkward. But initial versions of Memcheck, I think up to version 3.2, actually did this. Then Nick Nethercote came along and said, this is really stupid, and most bytes are either completely defined or completely undefined. This metadata is extremely boring and repetitive. And it would be better to have 2 bits per byte, which I'll show you a little bit later, I think, or is that the other talk? Basically 2 bits per byte, which is, it's accessible, not accessible, it's completely defined, completely undefined, or it's partially defined. And then if it's partially defined, that's what the epsilon is, then we look in another table to find out the exact definedness of it. But most bytes are either totally defined or totally undefined. So now we use this scheme. It also is much less data, and it means less pressure on caches. When to report undefinedness? This is another core decision. So one possibility, and the obvious thing to do, is you check every time you read memory, and if you pull an uninitialized value out, you say, oh, error. The problem with that is that you get thousands of false errors again, because, for example, GCC will copy a whole struct with holes with a word load and copy it to somewhere else, and just copy that uninitialized data around, and that's harmless. So that's no good. You need to do better than that. So what the system does now is to follow the uninitialized data all around the system, and only when it gets to an if statement or use it to generate an address does it say, okay, I've got to report this now. Because if I don't, then your program could actually fail. You could get an exception, a seg fault, and you wouldn't know why this happened. Can we make it multi-threaded? Well, it's kind of difficult because genuinely multi-threaded, I mean, because coordinating these detailed tables in a multi-threaded way is very difficult. So the answer is not really. The kludge we use is to sequentialize threads. So you can run a multi-threaded program, no problem, but Valgrind will actually cause only 1 thread to run at once. So we kind of dodged the issue. It's not a good solution, but it's what we have right now. So what do we learn from all this? Well, porting to new architectures is much easier than people think it is because instruction sets are well documented, and even if they're not well documented, you can run instructions on the hardware to find out what is actually really happening. And the VEX framework actually made it quite easy to do. It's still a lot of work because there's generally so many instructions. There's also been ports to different operating systems, so AIX was one that sort of came and went. That was difficult, and we have a kind of a macOS port which kind of sort of works, but is sort of in need of attention, I think. This is amazingly difficult to do because you have these undocumented interactions between the kernel and user space, and you need to deal with them. What we found for OS X and Linux is that you need to be able to read the kernel source code and the C library source code. And for AIX, I couldn't do that, and it made it nearly impossible, basically impossible to do a reliable port. What else did we learn? Users will do all manner of crazy shit, right? No matter what you think of, they think of something really bizarre else to do and some other way to break the system. Yeah. So what did the users think? Well, yeah. Oh, sorry. Yes. Yes. But this is another key decision. But this is not about Memcheck. This is about how the JIT actually works. So it's a system which takes blocks of machine code and produces blocks of instrumented machine code. And one way to do this is to take your original piece of code and copy it to the output and then add some extra annotations which check what you are doing. That's a copy annotate system. And that's what most frameworks like Pin and Dynamo Rio do. A disassemble resynthesize system, you take your original machine code, you transfer it into this intermediate representation, you instrument that, and then you generate new machine code. And that's what Valgrind does. So copy annotate is probably easier in a single architecture situation, but it has a serious disadvantage, which is that you cannot ever really check that your annotations are correct. Versions 2 of Valgrind actually did this. With a resynthesizing JIT, you are generating the new machine code from the intermediate representation, and if that intermediate representation is wrong, the program just won't work, and it's obvious that your instrumentation is going to be wrong as well. So I chose this for reliability, and also because it's probably more portable. Sorry. So what do users think? Well, it seems like it got used widely. Because it's open source, you can never really tell. I think the most effective users actually integrated it into their test system. So you run your entire test suite with Valgrind, if you can. It's kind of slow, but it will pick up all sorts of weird corner cases. They reported almost infinite number of bugs, which is like if you were sitting in the middle of this looking at all these bug reports, you think, whoa, the system's really buggy and broken, but I guess for most people it mostly works. They provide an enormous number of suggestions about how to improve it, a lot of patches and a lot of support in terms of people doing stuff and support for people to work on it one way or the other. And they did all sorts of stuff which I never expected. So we have people running user mode Linux. That was a thing a few years ago where you have a kernel running in user space and they wanted to run Valgrind on it. We have people running like big processes, like 100 gigabytes of memory. It doesn't work. Fix it, this kind of stuff. Okay. And people with 10, 20, 30 million lines of C++ stack sitting on this system, which I also never really expected. Well, it's kind of nice that people use it. So what else? What they didn't do is, which I really expected people to do, is to complain a lot about the slowness. So people sometimes complain how slow it is, but it's like mostly it just seems to be tolerated, which kind of surprised me in a good way. They didn't believe what it was telling them. So imagine you are in charge of some big C++ code base, and it's 2004, and you've never had one of these tools before. And you put your code base through it, and it says, yeah, there's all these errors. And you think, whoa, I think my code base actually works right, and I don't really believe this stuff. So we got quite a few people saying, I don't believe what it says, and then you get into some argument, and you say, show me your bit of code, and then you say, oh yeah, the problem's here. As time went on, I think this phenomenon has gone down because code bases have got cleaner as people use it more, and I think maybe there's a sort of a acceptance that probably the system is actually quite reliable now. One thing that was very noticeable is that this decision to delay reporting of memory errors, undefinedness errors, actually makes it extremely difficult to find where the original source of the undefinedness is. So at some point, this origin tracking thing was implemented. That allows you to at least find where your uninitialized allocations originally were, but it makes it even more slow. Another phenomenon which you can observe, which is kind of related to not believing it, is that imagine that this is the entire universe of all programs you could ever possibly have. And then inside this universe, like this, is the set of programs which are actually correct from a memory usage point of view, what Valgrind can detect. So people expect that if their program is actually correct, then Valgrind won't, or Memcheck will not complain about it. And that's almost true, but it's actually not completely true. So there's this small number of programs or fragments of code you can construct which are actually correct, but Memcheck complains, and they expected these two universes to be the same. So, you know, it still happens occasionally. We had one bug about this just the other day. And I have been trying to say, this is a kind of a verification system for C++. You cannot expect that every single correct program it will not complain about.
Could you give an example of something that it complains about that is actually valid? Because I don't fully understand.
Well, so just the other day we had an example where a person was using the byte just below the stack pointer for some locking purpose. And there was a long discussion in the bug tracker about, is this actually dangerous or not? And it's probably not dangerous, but Memcheck says you cannot access below the stack pointer because that's probably what the ABIs say. Another example is gzip or zlib. That has some weird algorithm when it's compressing, which is actually correct, but it uses comparisons on partially undefined words, and Memcheck complains about that. So that's kind of a bummer. Maybe I should rewrite it. Well, they should rewrite it.
Yeah, there are also simple things like you ask the kernel to read something in the buffer, and you give it
oh yeah,
a buffer that isn't completely addressable. And Memcheck will say, the kernel could read, and then people say, yeah, but I know if I read this, there won't never be more than 4 bytes.
Yes.
Yeah, that's don't give it a buffer.
Yes. Yes. So I kind of want to say.
But that I would say that's actually a bug that the user should address.
Well,
yeah, but if they know the files they read are always really small.
Yeah. Well, the message I would actually like to say to people is that if you want your program to be automatically verifiable by these kinds of systems, then you might have to accept that you need to write it in a slightly restricted subset of these weird behaviors in order that you have the verifiability. Because verifiability is not necessarily zero cost. Anyways, to move on, how much time will I have? How am I doing?
20 minutes.
20 minutes. Oh, I better speed up. Really, 20 minutes? Shit. Okay. So, sorry? I wanted to give a quick sketch of the design, but I'm not sure this is convenient. I'll speak really quickly. We have a core. The system is separated into a core which does a whole bunch of complex stuff, including jitting. And then we have this jitting pipeline, which is a simple compiler. So you take your original code, you transform it with a front end into the intermediate representation, and that goes through the tool, which whatever the tool is, and instruments it. And then the back end then transforms it back into executable machine code and sort of hooks it up with this chaining stuff so it can continue to run.
Can I use a different emitter than I use at the front end?
Well, that was one of the original design goals, and in fact, nobody ever implemented that. There's other problems like system calls if you do that, but in principle, yes. Another aspect of the design is that the intermediate representation is simple, so it's easy to write a tool. And also, there's these optimization passes which clean up the intermediate representation. So I'll come back to that. So this is a little example of it. If we have a x86 subtract instruction, then you have some bits of code in the intermediate representation which pull the values out of the simulated registers, add them together, and then put the value back in the simulated register. Or if you have a conditional branch, then we say in the intermediate representation, we're going to make a side exit based on the, some comparison result. And that's where we're going. And kind of similarly, if we have a load from memory, then we're going to fetch value from memory, fetch the address, and then we're going to do a load, and then we can put the value back. So over here, we have some instrumentation which Memcheck generates. So for this add, for every register, we also have a shadow register which tells you the definedness of it. So we're fetching these shadow values, and then we're doing this kind of interesting bit of computation. So we take the two shadow values. These are words which tell you the definedness of the actual values there. And we're doing this u if u primitive, which means undefined if undefined, so taking the worst case. And then we have another primitive called left 64, which simulates the worst case carry propagation. So qres becomes the value which tells you something about how defined the result is. And then we put it back in this simulated shadow register. And just as an example which is important, for this conditional branch, what we need to check that we're doing a branch on defined data. So we are then checking that the shadow value does not contain any undefinedness. And if it does, we're going to report an error. And this has to go, of course, before we make the actual branch. And there's more stuff, but time is short. So the other bit of the picture is that we have to track the status of memory. So we have, at least in the 32-bit case, this big basically a two-level array. You take the top 16 bits of the address and index into this table of pointers. And then you use the bottom 16 bits of the address to index into these secondary tables, which tell you the definedness for, well, basically they contain 64K worth of definedness information. There is there's a whole bunch of trickery which makes reads faster at the expense of making writes a bit slower, but it's a good trade-off. 64-bit is a terrible kludge because we really want to retain this two-level structure, but at least it's fast. It's a terrible kludge. I'm not proud. So what are the challenges that have emerged? Well, there's a bunch of problems, but one of the most serious problems are caused by compiler optimizations, and in particular the fact that GCC and Clang have taken to compiling conditional expressions like this in the wrong order. It's actually safe, but this is, you kind of have to really think about this, but it's actually correct transformation. It means that this code will actually do branches on undefined data, and Memcheck complains about that.
What are AMD in these?
Just arbitrary expressions. They are arbitrary expressions, yes. It is actually correct if you think about it long enough. I can tell you later. There's a couple of things that are quite concern-causing, one of which is the load linked and store conditional problem. So on every architecture except x86, we have a more modern way to do atomic memory accesses, which is important between threads. And one of the results of instrumenting it the way it's done is that you can drive the instrumented program into an infinite loop, because the atomic, the instrumentation that you put into this atomic looping pair causes the transaction to always fail. That's a serious problem, and we do not have a very good solution at the moment. We have some hacky solutions. As time is running short, I think I'm going to skip some of this. Gah. Okay. I should say I expected a couple of problems early in the project. So I expected compilers vectorizing code, vectorizing integer code to actually be a source of inaccuracy. But it turns out that compilers don't vectorize integer code very much. They mostly vectorize floating point loops. So that's not a problem. I was also concerned that this kernel interface, the Linux kernel interface, which is a big complex thing which we describe very carefully in the code, would change rapidly and cause a big maintenance burden, but in fact that's never been a really big problem. So to look forwards, I want to talk a bit about relevance, right? Because back in the early 2000s, this was really the only tool going which did this kind of memory checking. But now we have a whole bunch of what you could call sanitizers. So in particular, we have the LLVM-based, or now partially GCC-based, compile-in sanitizers, and they're a really good thing. They do a good job, and they're much, much faster. But they're also more limited because you have to compile stuff, and they can't deal with JIT-generated code. What all of these tools, the effect of all of these tools, if you take them together, is that they find lots and lots of cases in C++ in particular where the behavior is undefined. So we have, undefined value uses. For example, ubsan will find shifts that have undefined behavior in C++. There's a lot of that. So the effect of this is to really take a problem about finding undefined behavior in C++ and turn it into a code coverage problem. If you're really good at testing more stuff in your code, if you have more test cases, then you can find more bad stuff, more things that are going to cause problems later. But this is actually a huge amount of hassle, and it's incomplete, never complete, right? So no matter how much testing you do, you can never be sure that you're going to pick up everything. So what can we do instead? Well, we could do static analysis of C++, maybe. In the open source world, I don't think we have really any really good static analysis systems which are comparable with the commercial the state of the art of the commercial world. I'm not really sure about that. But basically C++, well, it's always going to be a safety problem because of the fundamental fact that you have no control over pointers. And look where we are now. So people spend enormous amounts of money and effort doing dynamic testing of big complex systems like web browsers or the stacks you have on Android or something like this. And we're still up to our ears, as a community in security problems, especially nowadays it seems. So maybe it's time to think of moving away from C++. I think there's a feeling that, especially with somewhat younger programmers, that the compromise that we've had to make with C++ from performance versus safety is increasingly a bad compromise, and we want to do something else. So I'd like to say, well, there are other programming languages, Rust, kind of from the Mozilla world, so I'll say Rust is a great language.
That's how you start.
Haskell, yeah, it doesn't have this one, right? So in my completely partisan view, Rust actually delivers what Haskell promised, minus the insanely inefficient execution model. So Rust is a language where you have a new idea, which is for the compiler to check mutability and to check your story about storage management, and if it can't come up with a valid story, then it rejects your program, which is actually a really great property. So I encourage you to look at Rust if you haven't done so. It's very cool. I think it's an idea whose time has come. But anyway, sorry.
And you can still use Valgrind for the unsafe segments. If you have an unsafe block in Rust, you can still use Valgrind.
Exactly. They do that.
You still have a job?
Well, I think I probably have a job, yes. But I think Rust is great. And to be serious, somewhat more serious, we have an enormous whole planet of C++, and that's not going to go away anytime soon. So there is scope for both of these things. So I'm nearly finished, but wanted to say that despite the appearance of these other checkers, Memcheck still has a kind of a unique niche. So it does high precision definedness checking, which I don't think any of the others really do. It can deal with JITted code, and it's really easy to use. So, what do we need to do as a Valgrind development community? Well, firstly, we really need to think hard about parallelizing the system as a whole. We've got away with this sequentialization for a long time, and it's been a good trick, but with multi-core systems everywhere, that isn't going to fly much longer. I can't actually think of a way to do this without some loss of sequential performance. I've done some initial studies about parallelizing Memcheck, and Philippe has actually done a whole bunch of initial hacking about parallelizing the framework as a whole. So that's a possible interesting avenue to explore. If you come back today, 3:30, I'll talk more about rearranging the JIT to have basically to have higher performance headroom. So we've, I think, cranked almost all of the performance we can out of the existing JIT, and it's time to think about a new framework. So that would help. We also need to do something about the increasing number of false positives that we're getting. So having a JIT which can analyze larger pieces of code might help that. Having people look at the definedness instrumentation would also probably help that. So that is all I wanted to really say. I would like to say thank you to everybody who actually made it work so well, the developers and the users and people who did auxiliary things like built the website and built GUIs and integrated it into their systems. We need your support for the next 12 years. I will be talking about VEX at 3:30, so please come. It will be cool. it'll be more technical. And are there any questions? Any more questions? Yeah.
Yeah, I was curious about register allocation when you turn your IR back into assembly.
Yeah. Yeah, there's a lot.
Can't manipulate the stack as a program, right?
So can you speak up?
The register pressure.
Yes.
When you do the assembly again.
Yes.
How do you deal with that?
Well,
Still.
yes, we have to spill. The spilling is not as bad as you actually think it was. Sorry, the question is, well, that's very good, Mark. The question is, when we turn the IR back into machine code, how do we do register allocation? And in particular, there's a lot more register pressure there than there is in the original code, because we have also all these shadow registers. Sorry. I'll talk about that more later, but we basically do a linear scan register allocation, and less spilling than you would think. Yeah.
What kind of test suites does Voltaic have?
Well, the question is, what kind of test suites does it have? Sorry. It has multiple different kinds. It has test suites which check the instruction simulation quite carefully, because we need accurate instruction simulation if you want to run programs with billions and billions of instructions. It also has tool-specific test suites which check that the tools detect the kind of errors they're supposed to do. They're basically a large number of small C programs which you run and get an expected result for. The system would be impossible to maintain without the test suites.
And at which point did you add these test suites? Because I guess you started without it.
No, you can't build a JIT without without the test suites, right? Even to get to main in Linux, it involves simulating probably hundreds of thousands of instructions. You need something that can test that.
What is the official pronunciation of Valgrind? Is it Valgrind or Valgrind?
I don't know. It's some Nordic word, right? You should ask a Norwegian person, or Swedish, or Finnish. Sorry, is Finnish Nordic or Danish?
So what does it mean?
Oh, it's the magic gates to Valhalla, which only the pure shall pass through, or something like that. There's a longer story, but it's a stupid story. Okay, well, thank you.